Question number 4 part A. Define strain. So strain is the extension divided by original length. So strain is the extension divided by original length. Then a copper wire of length 4 meter has a uniform cross-sectional area. So we have given the value of cross-sectional area. A tensile force of 18 Newton. So we have given the value of force and we have given the value of length. So this is the length, this is the area, and this is the value of force is applied to the wire. This causes the wire to extend by 1.4 millimeter. So we have given the value of extension, that is the x, and since we know the value of extension but it is in millimeter, so we must convert this to meter. Up to its limit of proportionality, calculate the Young modulus of the wave. So we know that Young modulus is equal to stress by strain, and we know that stress is equal to force per unit area divided by strain. Strain is the extension divided by original length, so force per unit area, and since we convert divide into multiply, so length and x would reverse. So length comes upward and x comes below. So force into length. So force into length by area into extension. So force, so we know the value of force, divided by area, so we know the value of area, and the original length is 4 meter. And what is the extension? So we know that 1 meter is equal to 10 centimeter, and 1 cm, 1 meter is equal to 100 centimeter, and 1 centimeter is equal to 10 millimeter. So 1 meter is equal to 1000 millimeter. So 1 millimeter is equal to 1 by 1000 meter. So 1 by 1000 meter, or 10 to the power minus 3 meter. So 1.4 millimeter is equal to 1.4 into 10 to the power minus 3 meter. So 1.4 into 10 to the power minus 3 meter. So after substituting the value, we get the Young modulus as 1.1 in 10 to the power 11. So 1.1 in 10 to the power 11. And you have to also remember that Young modulus, for maximum amount of time, that is the extra term, that is 10 to the power 11 comes. So that means there is a value at front, suppose 1.1 or 2.2 or 9.3, and it is obviously multiplied with 10 to the power 11. That is, when 10 to the power 11 is given, then we have to we know that it is Young modulus. It is for maximum time, it is Young modulus. And for chapter 1, that is physical quantity and units, and for estimation, you have to know that for estimation of Young modulus, suppose you have given two values, suppose 1.1 into 10 to the power 19, 1.1 into 10 to the power 12, and 1.1 into 10 to the power 11. Then what would be the Young modulus? So Young modulus would also obviously be 10 to the power 11. So since 10 to the power 11 is this, so this is our Young modulus. So Young modulus is multiplied with 10 to the power 11. Now for part 2, on figure 4.1, draw a line to show how stress varies with strain for a wire up to its limit of proportionality. So stress against stress, and for up to its limit of proportionality. So stress against strain up to its limit of proportionality. And since the wire does not reach the limit of proportionality, and this is the point of limit of proportionality, there is limit of proportionality. So before limit of proportionality, the graph have to be a straight line. So this is a straight line graph passing through the origin. So straight line graph passing through the origin. So whether it is a stress strain graph or a force extension graph, that is force against extension, the limit of proportionality is from the origin and it is a straight line. So from the origin and it is a straight line. And this is the limit of proportionality. For part C, a second copper wire has the same length, so the length is same as the wire in B, but a larger diameter. So the diameter is large, and since we know that area is equal to pi d square by 4, and since the diameter is more, so the cross-sectional area is more. So for the second wire, the cross-sectional area is more, that is area is more. Now both wires are subjected to a tensile force of 18 Newton, so the force is same. By placing a tick in each row, complete table 4.1 to compare the stress and the strain for the two wire. So stress, so what would be the stress? So we know that stress is equal to force per unit area, and since the value of force is same for both the wire, so it is same. And for the second wire, we know that the cross-sectional area is more, Since the diameter is more, so the cross-sectional area for the second wire is more. So since the cross-sectional area is more, that means the denominator is more. Since stress is equal to force by cross-sectional area, since the denominator is more, so the numerator have to be less. So the stress have to be less. That is, for the second wire, the stress is less, and for the second wire, what would be the strain? So we know that strain is equal to extension divided by original length. And since the original length is same, and since the original length is same, so what would be the extension? So here it is not given any value of extension, but we know that Young modulus is equal to stress by strain. So Young modulus is equal to stress by strain, and we know that stress is equal to force per unit area divided by strain. That is, strain is equal to extension divided by original length. So force per unit area into length by extension. And since the force is same, that is 18 Newton, and the original length is also same, that is, for the second wire the length is same, so length is same. But for the second wire, so for the second wire we can say that the area is more, so the diameter is more, so the area is more, so the area is more. Since the area is more, now for the Young modulus, so Young modulus is always a constant, so it is constant, or the Young modulus is same. Since the Young modulus is also same, force is same, and the length is same, so if the area increases, the extension must decrease. Because if we just rearrange, then the equation would be that extension is equal to force into length by area into Young modulus. So area into Young modulus, and force is same, length is same, Young modulus is same. So if the area increases, then the extension obviously decreases. So the extension for the second wire is less. Since the extension is less, so the extension value is less. So strain is equal to extension by original length. Since the extension is less, so the strain for the second wire is less. So the strain for the second wire is less.